And another method to estimate between two probability density function to find the gap is p-Wasserstein distance. Unlike the Coulomb library distance, that is really satisfies this metric axiom. So it is reasonable name to distance. Okay, but the definition is so abstract to understand. So in this lecture, I will explain what is the p-Wasserstein distance. But to understand this concept, if we introduce a tropical geometry, in the seventh lecture, lecture 7, a tropical projective torus, the next concept, projective torus, Rn R1 denoted by here, we can understand p-Wasserstein, the definition of p-Wasserstein metric at the concept of the p-Wasserstein metric well understand, because some people p-Wasserstein distance is called a optimization transportation optimization. Then if we consider this concept, we can understand what is optimization, transport optimization sense. We can understand a tropical p-Wasserstein metric as a transport optimization. Even if I will introduce the definition, but that is so abstract. Let's go ahead. For any two real valued random variable x and y with point probability density function fx and fy is given, then a p-Wasserstein distance between x and y. Anyway, note that even if these definitions are so abstract, the essential is to estimate probability, to gap between two probability between x and y. So it is given written as WPXY, that is infimum in that case, F is all collection of joint probability of x and y with marginal distribution fx and fy. We can take between all collection of probability density function blah blah blah, take an infimum of f defined as fxy, xy, xy, p, dx, dy. That is in fact a LP norm space. Okay. Anyway, if you understand that is one way to estimate between two gap. It is so abstract. Okay, that is natural. That is obvious to that definition is so abstract. About that, as I said, in the next lecture, by introducing practical projective torus, I'll explain why this is a reasonable definition as an optimalization between two probability functions. More abstractly, in case of the Kullback divergence, we can define generalized by introducing a probability measure. Likewise, we can define, in a probability measure, we can define p-Wasserstein matrix. So in this case, let X be a matrix space that is a Radon measure, Radon space. Not one remarkable point is that a Radon space is a measure space between on measure space on topological space. By auto-measure process, as we saw the definition, previous definition, if a topological space is given, we can define a Radon measure space. The interesting point is that this space is topological spaces. The definition, the construction is a little different with the general of the set X, but we can anyway construct a measure space, a Radon measure spaces. And of course, the metric induces a topology, okay? So we can construct a Radon space. Okay. Anyway, Radon space is just we can understand a measure space on a topological space. Okay. And consider like this. Then for any two marginal measures mu and nu on X. In the case, as I said, probability random variable exchange day measures the p-Wasserstein distance or matrix between mu and nu is given by mu and v. In the case, that guy is set of couplings of mu and nu, and the gamma, small gamma, is a joint probability measure product space whose marginal mu and mu respectively. Anyway, I know the definition is so abstract, but I will explain the definition of the p-Wasserstein matrix, and in this lecture 7, next lecture 7, by introducing Picot projective torus, I'll explain what is related to optimalization. That seems does not to be as I know that I understand that is between the gap between two probability density or two probability measures, but it's so abstract. But by introducing tropical projective torus, I'll explain why this is a reasonable definition as a optimalization, transport optimalization.